Hello, this is lecture 4 of chapter 1 and we will first read the table 1.2, and here we have what is the technology and what is the scientific principle that make that technology work. Maybe this is not useful for means NCRT student, but if you are preparing for any government job or anything, you should remember this. And any quiz competition, especially you are going for any quiz competition, that will help a lot because I went into one and I reached at in top three, but I'm not able to qualify at the regional level. So first, I will read all this technology and scientific principle. Steam engine, law of thermodynamics, nuclear reactor, control nuclear fission, radio and television, generation, propagation, and detection of electromagnetic waves, computer, digital logic, lasers, light amplification by stimulated emission of radiation, production of ultra-high magnetic field superconductivity, rocket propulsion, Newton laws of motion, electric generator, Faraday law of electromagnetic induction, hydroelectric power, conversion of gravitational potential energy into electrical energy, aeroplane, Bernoulli's principle of fluid dynamics, particle acceleration, motion of charged particles in electromagnetic field, sonar, reflection of ultrasonic waves, optical fibers, a total internal reflection of light, non-reflecting coatings, thin film optical interference, electron microscope, wave nature of electron, photocell, photoelectric effect, fusion test reactor, magnetic confinement of plasma, giant microwave radio telescope (GMRT), detection of cosmic radio waves, Bose-Einstein condensate state, trapping and cooling of atom by laser beams and magnetic field. So now we will go to the fundamental laws of physics. Means it can come in any exam like CDS, FCAT, I will say, NDA. Also, you can get many of this question as a general knowledge question. Now we will go to the section 1.4. We all have intuitive notation of force in our experience. Force is needed to push, carry, or throw objects, deform, or break them. We also experience the impact of forces on us, like when a moving object hits us, or we are in a merry-go-round. Going from intuitive uh, notion to the proper scientific concept of force is not a trivial matter. Early thinkers like Aristotle has had wrong ideas about it. The correct notion of force was arrived at by Isaac Newton in his famous laws of motion. He also gave an explicit form of force for gravitational attraction between two bodies. We shall learn these matters in subsequent chapter. In the macroscopic world, besides the gravitational force, we encounter several kinds of forces: muscular force, contact force between bodies, friction, which is also a contact force parallel to the surface in contact. The forces exerted by the compressed or elongated spring and taut strings and ropes, tension, the force of buoyancy and viscous force when solids are in contact with fluids, the force due to pressure of a fluid, the force due to surface tension of a liquid, and so on. There are also forces involving charged and magnetic bodies. In the microscopic domain, again, we have electric and magnetic forces, nuclear forces involving protons and neutrons, interatomic and intermolecular forces, etc. We shall get familiar with some of these forces in later part of this course. The great insight of 20th century physics is that these different forces occurring in a different context actually arise from only a small number of fundamental forces in nature. For example, elastic spring force arises due to the net attraction repulsion between the neighboring atoms of the spring. When the spring is elongated, compressed, this net attraction repulsion can be traced to the unbalanced sum of electric forces between the charged constituent of the atom. In principle, this means that the laws of derived forces such as spring force, friction are not independent of the laws of fundamental forces in nature. The origin of these derived forces is, however, very complex. At the present state of our understanding, we know for four fundamental forces in nature, which are described in brief here. I will first read about, before going to the fundamental forces, I will first read about the little bit means biography of this man, Albert Isaac Newton. Albert Einstein, born in Ulm, Germany in 1879, is universally regarded as one of the greatest physicists of all time. His astonishing scientific career began with the publication of three path-breaking papers in 1905. In the first paper, he introduced the notion of the light quanta, now called photons, and used it to explain the features of photoelectric effect and the classical wave theory of radiation could not account for. Actually, the photoelectric effect cannot be explained with the wave theory of radiation. At that time, the wave theory of electron is the most prominent idea about the electron, and the means the light, how the electron is. Everyone believed that electron is a wave at that time. And what is the atom? Atom also everyone believed that it is a wave. In the second paper, he developed the theory of Brownian motion that was confirmed experimentally a few years later and provided a convincing evidence of the atomic picture of matter. The third paper gave birth to the special theory of relativity that made Einstein a legend in his own lifetime. In the next decade, he explored the consequences of his new theory, which included, among other things, the mass energy equivalence. Einstein, in his famous equation equal to mc square, here is energy, m is equal to mass, and c is the speed of light. He also created the general vision of relativity, the general theory of relativity, which is the modern theory of gravitation. Some of Einstein's most significant later contributions are the notion of stimulated emission introduced in an alternative derivation of Planck's blackbody radiation law, static model of the universe which started modern cosmology, quantum statistics of a gas of a massive bosons, and a critical analysis of the foundation of quantum mechanics. The year 2005 was declared as uh, International Year of Physics in recognition to Einstein's monumental contribution to the physics in year 1905, describing revolutionary scientific ideas that have since influenced all the modern physics. Gravitational force 1.4.1. This is the first force we will see. The gravitational force is the force of mutual attraction between any two objects by virtue of their masses. It is a universal force. Every object experiences this force due to the every other object in the universe. All objects on the earth, for example, experience the force of gravity due to the earth. In particular, gravity governs the motion of moon and artificial satellite around the earth, motion of the earth and planets around the sun, and the motion of bodies falling off to the earth plays a key role in the large scale phenomena of the universe, such as formation of evolution of star, galaxies, and galactic clusters. One has to look into that. This gravitational force is a very long range force because the mass is the virtue of body. Charge may be neutral. A nuclear force is very short range force, but gravitational force is a very long range force. So because everybody has a mass, so if somebody has a mass, the gravitational force will apply between them. But we must not consider that there are only two bodies. We have to account for all the bodies around us, and so the net force will be the superposition of all the forces. And how this superposition will be added? This will be added through the vector addition. You must not count only the scalar wave, because scalar wave will be only helpful if both the object is in the same direction, in the same line to which it is applying the force. But in the other case, in any other geometry, the gravitational force, if you look, it is the sum of vector product. Electromagnetic force. The force is a vector quantity. I say that. So if its addition will be vector addition. Its addition will not be the scalar. While energy is a scalar, so you can add the energy of the many particle of the many forces applied on that body. But the force is a vector product, so a vector quantity force, so its addition will be vector. I will read just electromagnetic force, and after that we will stop from the electromagnetic force. Electromagnetic force is a force between charged particles. In the simpler case, when the charge are at rest, the force is given by Coulomb's law, attractive for unlike charges and repulsive for like charges. Charges in motion produce magnetic effects, and magnetic field give rise to the force on a moving charge. Electric and magnetic effects are in general inseparable, hence the name electromagnetic force. Like the gravitational force, electromagnetic force acts over a large distance and does not need any intervening medium. It is enormously strong compared to gravity. The electric force between two protons, for example, is 10 to the power 36 times the gravitational force between them for any mixed distance. But the problem is that we cannot have that much proton and at a single place, because they will repulse each other. The difference between gravity and electromagnetic force is uh, two masses never repel each other, but two charges repel each other. So it is very difficult to have that much amount of electron or proton at the same place. Matter, as we know, consists of elementary charge constituents like electrons and protons. Since the electromagnetic force is so much stronger than gravitational force, it dominates all the phenomena at atomic and molecular scales. The other two forces, as we shall see, operate only at nuclear scale. Thus, it is mainly the electromagnetic force that governs the structure of atom and molecules, the dynamics of chemical reaction, and the mechanical, thermal, and other properties of materials. It underlines the macroscopic forces like tension, friction, and normal force, spring, force, etc. It underlies means these forces are a slightly bigger level, but at the chemical and molecular level, you can see that this force is very dominating, and it decides means the shape of electron cloud around the atom. Gravity is always attractive, while electromagnetic force can be attractive or repulsive. As I say, another way of putting it, that mass comes only in one variety. There is no negative mass, but charges come in two varieties, positive and negative charge. This is what makes all the difference. Matter is mostly el- elec- matter is mostly electrically neutral. Net charge is zero. Thus, electric force is largely zero, and gravitational force dominate terrestrial phenomena. Electric force manifests itself in atmosphere where the atoms are ionized and leads to the lightning, as we see in during rainy season. Why? Because due to ionization. If we reflect a little, the enormous strength of electromagnetic force compared to gravity is evident in our daily life. When we hold a book in our hand, we are balancing the gravitational force on the book due to the huge mass of the earth by the normal force provided by our hand. The latter is nothing but the net electromagnetic force between the charged constituent of our hand and the book. At the surface in contact, if electromagnetic force were not intrinsically so much stronger than gravity, the hand of the strongest man would crumble under the weight of the feather. Indeed, to be consistent in that circumstance, we ourselves would crumble under our own weight. We can see that how means our normal weight balance our body. Strong nuclear force, and then we will in the next chapter we will go to 1.3, 1.4.4, 1.4.5, and I will read up to here table 1 means 1.5 section. For now I will close this lecture.